what we basically are doing is separating the patients by their gene expression. In this case, we are separating the patients by their expression in ARF3 candidate gene. So we take the patients with the highest, 30% patients with the highest expression in ARF3, and 70% of the patients with, the lowest, quote, with the lowest or the rest of the expression, not the highest, basically. So, patients with we have the initial number of patients, 30% of the patients with high ARF3, it's 572 patients, and 70% of the rest of the patients are 1,332. And then you check when they died or not, or we stopped following them. And we basically create a survival graph, also known as Kaplan Meier. Its p-value is taken by the log rank test, and we basically check the survivability of the patients in over 10 years, over a period of 10 years or 120 months. And I've done, and you have, here you have 4 types of separations. I separated the patients with by expression when they had 30% of the patients with the highest expression in ARF3, 30% of the patients with low ARF3, and then 20% patients with low ARF3, and 20% patients with high ARF3, and here it is, okay? And then we do that for each and every candidate gene, including MET, okay, including our driver gene. Your driver gene might be different. In our case, it's MET. Okay, and we check whether it's significant. Okay, so what we also do is we check for survivability with co-expression. And what I mean by that is that we separated groups. We take the patients and I separate them by their expression in MET and in another candidate gene. Here, for example, you have ARF3. So what I do, it's Kaplan Meier of gene 1, which is MET, and gene 1, we basically separated patients by 20% patients with high MET and the rest. Okay. We also separated the patients by gene 2, which is the candidate gene. Here it is ARF3, and it is also we separated that we separated the patients by 20% of them with high ARF3. What we got here, we got 2 groups. Here we got 2 groups, and then we made intersections. We basically made a Venn graph. Oops, we have perhaps it would be better to do something like okay, so yeah, let's not consider this one. So we have patients with high, I don't know, candidate gene, and let's call it ARF3, and we have the rest of the 80% of the rest of the patients, and these are mutually exclusive groups. But now we also separated inside. We also have groups with, let's say, rest 80, high 20. We also separated the patients by MET, our driver gene. Okay. Inside each such 80 inside each mutually exclusive group. So basically we get four groups overall. I hope you've followed. I know it's a bit confusing. Okay, so you have here you have high. Basically it means patients with high MET expression and high ARF expression. High in MET and the rest in ARF. The rest in MET and high in ARF. Rest in MET and rest in ARF3. We have four groups, and we want to see again their p-value and whether it's better than the p-value that was calculated by Kaplan Meier analysis when done on MET alone and ARF alone. Okay, and as you can see, this is the p-value. Now I do all the combinations possible. For example, here what is changed, we left the MET here the same, high 20% MET and the rest 80. But here with our candidate gene ARF3, we have the rest are 80%, and we take 20% patients with low ARF, and it's different. So here is high rest, high low, rest, 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 low. Okay, and our p-value got even better. Okay, don't save. And just so you know, so we have here MET high 80. We also have calculations with 30 versus 70s, but usually in our lab we only take the separation of 20 versus 80. Okay, and let's take the two more relevant calculations in ARF. Okay, so we have, now we take low percentage, 20% of the patients with low MET versus rest in MET. And here in our ARF, we have a high 20, rest 80. Okay. And here again, 20% of the patients have low expression in MET, and we changed in ARF3. We also take 20% of the patients with low expression in ARF3. Okay. And the p-value is calculated by log rank of survival, by long rank test for multiple groups, more than 2 groups. Another thing, yeah, okay, so let's check if our calculations was done. And yeah, our calculation was done. Here you can see the names of the graphs that were outputted, and once the code is done, you have done here. Okay, so let's go for our test file. Here you see, here's what I talked about before. You get a directory that's called graph, graphs, okay, and you get the same type of calculations that I talked about before. Okay, and you are supposed, with this type of calculation, you are supposed to get 8 graphs. 4 of them are relevant because you get you only look at the calculations with the 20 versus 80%. So you have Kaplan Meier analysis KM, MET, which is the driver gene's name, versus candidate genes, and you have gene 1, which is MET, which is the driver gene. And in this calculation, we took the 20% high patients, patients with high in MET, and the rest 80. Gene 2 is the candidate gene, and we also took high 20, rest 80. And let's look at this file, for example, page layout. So here you get where your data was taken from, what is your clinical data, and in row number 3, you get the driver gene's name, high percentages that we took, the low percentage. So we took 20% of the patients had high expression in MET, and the initial number of these patients are 381 initial numbers of patients. Here it's written low because I couldn't really change the word to rest, but it doesn't really matter. So the initial number of 80% of the patients is 1,523, and overall we had 1,904 patients. Okay, and the p-value, what if you do the Kaplan Meier analysis of when you separated the groups by MET alone, and the p-value is 0.007, which is significant. Okay, we actually want our results not to be significant in our driver gene, because we want our results to be significant, when our co-expression happen, but it doesn't really matter. Go with the old version. Okay, so we got this p-value of, this p-value of Mat, and okay, when you compare Mat with tuba AC1 or other candidate genes, and I wrote, okay, I wrote the high percentage of gene 1, low percentage of gene 2. Here it's rest. High percentage of gene 1 of gene 2, low percentage of gene 2. Here it's rest. Initial numbers of patients high. It's 156. Initial number of patients high low. Low high. Low. Here is rest. Okay, I could not change a L to R. It was just too cumbersome and not really necessary. Okay, so the p-value of the co-expression, this is the co-expression of when you look for, let's candidate genes graph, and then you have tuba AC1. No, this is not co-expression. Okay, this is co-expression, and we're looking for tuba AC1. High, yes, this is our requested, and it's 0.0007, and voila, this is our p-value. This is the co-expression p-value. Okay, is it significant? Yes, it's significant. And why is it significant? Because it is smaller than 0.05, obviously, and it's also smaller than the p-value of Mat. Good. And let's see, false. Okay, so as you can see, ARF5 might be smaller than 0.005, but it's not smaller than the p-value of Mat. Okay, so I also included the p-value of just the expression of each candidate genes. And by that, I mean tuba high, right? Yeah. This is just expression that when the patients were separated just by the expression of tuba AC1, and you see the p-value is 1 multiplied by 10 and with the in the power of -4. Yeah, this is the p-value, and it's significant. Yeah, it is significant because it's smaller than 0.05. And what you want to do is do this. You want to check whether M, you know what, you want to check whether this is bigger than this, whether the expression the p-value of the calculation of Kaplan Meier analysis with just the expression of the candidate gene is bigger than the p-value of the calculation when we do just when we do a co-expression, when we take Mat or the driver gene basically and the candidate gene. Here it's 2 by AC1. Okay. And no, it's not bigger. So let's let's see if we have something bigger. And yes, wow, we have an ARF, or in CAPN 13, we have the p-value of just the expression of CAPN 13 is much, much bigger than the p-value when we do co-expression. Okay. And also, the good news is that the co-expression is significant, and it is better than the p-value with MET alone, and it is better than the p-value of the candidate gene alone, of CAPN 13 alone. So what we can do is write this. If, okay, if and if okay, we'll do this smaller than, if the co-expression is smaller than 0.05, and the MET's p-value, or the driver's Dean p-value, is smaller than, it is also smaller than K5. And also K5 is smaller than, the co-expression is smaller than the expression of the candidate gene, then we say write true, else write false. Okay. And you get all the candidate genes, which are good, but we also wait, 0, 1, wait, it's not supposed to be like that, because, oh, it's not 05, it's M. Sorry. So that, and you get not so many candidate genes which are basically significant in our case. Also, let's look at PAX4 here. Let's look at PAX4. PAX4, when it's high MET and high PAX4, okay? High MET, high PAX4. High 20, high 20, okay. High P and PX, okay, this. Okay, so let's look at the groups. So we have certainly, our blue is when only the patients which are high in MET and high in PAX. Okay, so yeah, we can see that the survivability is lower here in comparison to the other groups. Okay, let's look, for example, what happens when PAX is high, but MET is the rest of the patients, which is yellow. It's here. It's no different than the other groups. What happens when, for example, we have high MET, but we take the rest of the patients in PAX? So high rest, it's red, so it's close to the yellow line. And that's good. So that's a good graph. Okay. So let's say that you want to work on this graph and you want to take it in your calculation. What you will have to do, you have here its fig file. Okay, and let's copy the path. So fig name. Fig name is this, properties. Copy. We're copying that. Copying that. Okay, we have fig name, and now let's do open fig and fig name. Visibility will be visible. And we're opening the file. Now, while the code is running, what I did in order for the code to run faster, I hid all the figures. So once you open the figure, you have to change its visibility to visible, because its visibility, when it was saved, it was hidden. Okay, so here, tools, edit plot. And now you can play with whatever you want to edit. For example, let's say that you want to change this legend and you want to make the line width bigger. Voila. Line width 3, line width 3. Okay, and what you can do, for example, is font. You can change the font to whatever you want. I usually like this font, and I do this, and I also enter. Voila, you have a better file. You have a better graph, a better looking graph. Save as. So I'm gonna save. I opened specifically an edited directory for edited graphs directory, and I save it in two versions, one in fig version, so you will be able to work on the figure later on from the point where you edited it, the plot. And I'm also saving it as a PNG or TIFF or any other non-compressed image extensions. Graphs edited. Let's look at our edited graph. It was PAX. Voila. This is our graph. We can change it. You can change it however you want it to look like. You can even change the color of the lines. And now, this is something that is, you can say, prose in Matlab. It doesn't matter in which programming language the code was written, whether it's Python, R, or Matlab, it doesn't matter. but the main pro for Matlab is that you can easily edit the graphs and you don't have to recalculate everything all over again. So that's a plus. Okay, so that was an explanation regarding Kaplan Meier. Should I save it? Let's save it. If you want more explanations, here you have, for example, here is Kaplan Meier analysis, MET versus candidate genes. Gene 1, which is MET, is rest 80, low 20. Gene 2 is high 20, rest 80. And if you look at it, this is not true. If you look at it, it's very similar to the other calculation, the other table. So we basically, you have to look for four files. These are your full files with the 80 versus 20 separation. Why was 20 versus 80 chosen? Just because it's a thumb rule. Apparently, it can be changed in the code itself. Yeah, okay.